Hello there, welcome to this presentation from SciMed. Today we're going to show you about the benefits of on-site oil analysis using the Spectro Minilab platform that you see behind me here. So it will consist of a short presentation about the benefits of oil analysis, a bit of a drill down into the technologies behind these instruments, and then a real-time analysis of an oil sample to show us how quick and easy it is and how quickly you can get the results. So I hope you enjoy it. Thank you.
Hello and welcome to the video. Today I'm going to be discussing the benefits of on-site oil analysis for industrial plant machinery. My name's Malcolm Haig and I'm a product manager for SciMed Limited. So a little bit of word about ourselves and our principal, one of our principals, Spectro Scientific. We are a 40-year-old company specialising in the distribution of analytical instrumentation, primarily in the UK. We represent major international instrumentation manufacturers, all of which on an exclusive basis, and we are totally responsible for all sales and after-sales support activities. Spectro Scientific are a US-based company. They were founded in 1981. They're the largest turnkey oil analysis solutions provider in the industry. They're a major US and NATO defence contractor, and they supply condition monitoring of equipment to the defence forces. Now, if we look at the machine condition technologies available now, we see a whole range of them, of which oil analysis is part of. It is a vital part of this, but you do have other techniques that go hand in glove with it, like vibration, ultrasound, infrared, thermography, etc., etc. So we're going to be focusing on oil analysis. Where is it best to detect a problem in a industrial asset? Well, there are several places you could detect it, depending on what techniques you're using. Obviously, one of the final ways of detecting it is when it breaks, right at the bottom here. But we would like to detect our problems as early as possible before they manifest themselves into critical failures. And we can do that by analysing the oil. In fact, oil is the lifeblood of your critical assets, and its condition can tell you an awful lot of the situation that you find yourself in. So it's actually like the two sides of a coin. You've got the condition of the machine, is it healthy, what's wearing, that sort of thing. You've got the condition of the fluid, is it fit for use still, or has it degraded, or indeed the situation with the contamination that you might find in there. Is the oil clean, is it dry, etc. So what we're trying to do is increase asset availability and reliability, and therefore its return on investment, by reducing unplanned downtime, increasing the asset life, increase the utilization of that asset, and reduce risk of catastrophic failures, all of which reduces operating expenses, and finally enhances productivity, which is what I think everyone is keen to do these days especially. So traditionally, oil analysis has been subcontracted to outside labs. There are several scientific disciplines used in the production of your single oil analysis report. Perhaps recipients of these reports don't realise that, but there's a whole bank of equipment that goes into making that one report. However, sending samples away causes time delays. It's bad enough for fixed assets, but even worse for mobile ones, because if you, for example, have a train or a bus brought in for regular service, quite often an oil sample is taken, that's sent away to the lab, the train is finished the service, it goes back into its routes, then a report comes back saying that there was a problem with it, and then that asset has to be brought back to the workshop for an urgent repair. So it's not really efficient. Now, the various oil condition monitoring techniques have been brought together into the Spectro Minilab concept, which is a modular platform a series of platforms for industrial and also automotive assets, and we'll look into that in the next few slides. So the Spectro Minilab on-site workshop-based oil condition monitoring platform. Looking at the picture down below, we see a Minilab 153. It delivers comprehensive on-site oil analysis results in less than 15 minutes. It's designed for maintenance technicians. It gives lab quality analysis results right in your plant, right at the point of sample. Not only that, but it provides results, diagnostics and maintenance recommendations. It is powered by the TrueView 360 database software, a single or multiple site overview for group-wide managers. So the TrueView 360 enterprise platform is kind of a new approach. It consists of two parts. We have the instruments, the actual instruments themselves, and what we call the device console. This is the part of the software, or a separate part, package indeed, that actually drives and controls the instruments. And then the actual TrueView 360 software for the collating the data and applying rules and reporting. So it's a perfect tool for condition-based monitoring reliability teams. Why? Because it provides automated diagnostics, recommendations based on alarm thresholds, and these are adaptive to the life of the oil and machine rather than just arbitrary limits. So as you see from the diagram on the right here, we have the instruments connected to the device console, which drives these instruments. The results produced by the instruments are then fed up as raw data into the cloud or a local server, depending on how you want to operate, and that can then be uploaded into the TrueView platform. Now that might be in a different site. You may be a manager responsible for several sites and many assets, and you have an overview here. In fact, if required, you can schedule maintenance this way to then feed down to the device console, to the operator there, to actually do the tests and then report the data back. So it's a totally integrated solution for a predictive maintenance program. So let's take a deeper look at the platforms. As it says, they are modular, so you don't have to acquire the whole set. This is a Minilab 153 that you're looking at, with an elemental analyzer, which will give you 24 wear elements at very low levels in parts per million. There is an option for 31 if you have exotic bearing materials like our friends in the Formula 1 race team environment. You have here a laser particle counter. It's not just a particle counter that gives the traditional ISO cleanliness codes, or other codes are available, but it also images the wear particles and shapes them into the classical wear shapes like cutting, sliding, fatigue and that sort of thing. Then it will give you total ferrous particle count and also the large ferrous particle count, which is very useful information to have. Next, here is the fluid scan infrared oil analyzer. This is the one that will give you the oil chemistry, such as total acid number, TAN, or base number, or TBN, water, fluid integrity, other parameters as well, like oxidation and so on. And finally we have a viscometer. So that's going to give you kinematic viscosity at 40 degrees and a calculation of viscosity at 100 from the viscosity index of the fluid in question. So all of this will give you a full oil analysis report in less than 15 minutes, and they are ASTM compliant as well, details of which to follow. I will just mention down at the bottom here, depending on if it's industrial plant or automotive assets you're looking for, you can get additional tests for example, fuel dilution or total ferrous as well. So it's quite modular. So the methods that we use, I think I remember saying in one of the very first slides that a traditional off-site lab has many scientific disciplines employed to produce all of these results. So the techniques we use for elemental analysis, we use a technique called rotating disk optical emission. It takes 3 mils of oil. It produces 24 or 31 elements simultaneously in 30 seconds. No sample preparation, no chemicals, no gases, unlike the traditional lab type wear metal analyzer. Then we look at the particle counter. Takes 10 mils, takes a couple of minutes. It gives, as I mentioned before, particle count, shape classification, large and total ferrous. The infrared takes 20 mils of oil and it produces a result in less than a minute. Now if you're not sure what 20 mils of oil is, it's a drop. And it produces the oil chemistry parameters that are very important to decide whether that oil is still fit for purpose or has it been contaminated by, for example, water. Again, no solvents required. Viscosity 60 microliters, 30 seconds to 5 minutes. Now that depends on the actual viscosity of the oil in question. The thinner the oil, the faster it will produce a result. The thicker the oil, up to a limit of 680 centistokes, it'll take a little bit longer because it's a gravimetric technique. If you have the automotive system with the interest in fuel dilution, that takes half a mil and it's roughly a minute to give you fuel dilution in the range of 0.2% to 15%. And the total ferrous analyzer is 1.5 mils in less than a minute. All of the tests are ASTM compliant. There are the ASTM numbers on the right hand side there. So let's look a little bit more in a bit more detail about the two parts of the software. So here we have a screenshot of the device console. So you'll see that you've got the elemental analysis and the little ready box, viscosity ready, infrared ready, and particle analysis ready. Just click on the little arrow button and that will guide you through the process to produce the report down here. Now this is just not the final report, this is the instrumentation report, which is then uploaded up to the TrueView platform to be viewed by remote site managers and that sort of thing. You can also have the images here, which are the wear images that are produced, and even color images if you wish to take a picture from the inbuilt webcam. The device console also has some very useful onboard tutorial videos. If you have a situation, as we do with our customers in the military, where you have a rotation of staff, so no sooner is someone trained up and used to the equipment, they might get deployed somewhere else and someone else has to take over. So these onboard tutorials take the user through step by step how to actually go about doing the tests. It's very handy to have. Now we look at the TrueView part of the software, more or less the heart of the whole thing. On the left here we have what we call the asset tree. Now this is basically the how your plant is organized. It might be the main site, subsidiary sites, and the various different assets that you have there. So for example, here we have an engine and a sampling point, then we have a transmission and a sampling point, and this is entirely constructed by the asset owner. This is your responsibility because it varies from site to site. Then we have a dashboard where you can do diagnostics and looking at historical performances, and it's very, very flexible. And that's the sample list there. So the TrueView dashboard is quite a very handy tool for looking at continuous improvements. You can actually put in there savings, for example, savings on not putting fresh oil into an asset that doesn't need it. So all of that can be added in to give you a better overview of your situation. You can have various sites, single site, right down to the asset and so forth. and a lot of metrics inbuilt for producing viable data to make decisions on. Okay, here is the actual report that is produced. It uses the trivector indicator, which is a very useful instant pointer to what's going wrong with the asset. In this case, we see we're looking at contamination as being the main issue. So all the results down here, it's very difficult to see on this slide, so we'll actually go and look at that in a bit more detail. So I'll turn the page. So looking at the top of the report, as you saw before, the trivector is pointing to contamination. We have some sample identity information here, but what we have is the observations. So the reason that the trivector was pointing to contamination was that the particle count was severely high in the greater than 4 and greater than 6 micron ISO codes. There were some diagnostics put down here and some recommended actions. Now that's all done by the software, and this particular report, obviously we're looking at one report here in the blue boundary, but the historical earlier sample analysis are in the history, and we've got a nice indicator saying you have a problem, call the boss. Conversely, here is a good oil sample, one that is not showing any untoward problems. So you've got a nice green tick, you've got observation which is saying everything's below alarm limits, you're okay, no actions required apart from a resample at a regular interval. So if we put it all together, it's a simple and holistic approach to oil analysis. What normally happens is the samples are scheduled by the TrueView software, sent down to the operator with the device console. He produces the results, he runs the tests, sends the sample up to the TrueView, and decisions are taken and metrics are created. Very, very flexible. So in summary, we have lab quality data on site without a traditional lab. There's some images here of where these have been installed, and as you can see, these are not laboratory situations, these are workshops. These are workshop personnel using them, and they require no special installation requirements. You could run one in your house if you wanted to. So it's benchtop, all benchtop, just an office or a workshop environment. Nothing's cheap in science, but about half the cost of a full-size lab. Takes, as we said, less than 15 minutes per sample, depending on which platform you have. 15 minutes is for the full 153 platform. No need for laboratory staff. It is designed to be used by technicians, maintenance technicians that is. As I mentioned before, we have military technicians using them as well. Very quick to get up and running. Within a week you're producing results, and very, very small consumable use. Thank you for that. I'd like to just give a few quick acknowledgements to Martin Williamson of Q Engineering for one of his slides. Q Engineering are lubrication and reliability consultants. There's their website if you're interested. To Dan Walsh and his team at Spectro Scientific for the bulk of this presentation that I've shown you, and that's Spectro's website there. And to the following people who kindly supplied samples for the live demo, which we'll move to in just a minute. Craig Cousins of Fast Filtration, they're cleanup specialists, that's their website. Chris Marfell of Branch Hydraulic Systems, they're suppliers of hydraulic equipment supplies, that's their website. Andrew Thompson of Nissan Technical Centre for supplying a sample, and Kevin Harrison of CFCS, their on-site fuel analysis company and cleanup specialists. So now is the real-time demonstration. Thank you.
Okay, having looked at the presentation, now let's look at the instruments in a bit more detail. What you're seeing here is what we call the Spectro Minilab platform. It's modular. This particular outlay here would be called a Minilab 153. So we have a wear metal spectrometer, which will do 24 wear metals in about 20 seconds. We have a viscometer, which gives kinematic viscosity at 40 degrees and calculates that of 100 degrees if you know the viscosity index of the fluid in question. An infrared analyzer for the oil chemistry, for things like total acid number, total base number, water, etc., etc. And a 4-in-1 particle counter. Now this one will count the particles. Anything from 4 microns up to a cutoff of 100 microns will be counted, and then displayed the results in total counts and also in the ISO codes or other codes if you wish, like NAS or and so on. Then it will image the particles and categorize them into their classical wear shapes, like cutting wear, sliding wear, fatigue wear, non-metallics even, and even fibers. It's a very useful diagnostic tool. Finally, it will give a total ferrous debris analysis and also a percentage of large ferrous as well. The reason for that is that the wear metal spectrometers, and that means all of them, this particular one greater than 10 microns. The commercial oil labs use a technique called ICP. This is called RDE, rotating disc electrode, and they can't see much more than 5 microns. So if you've got big iron particles, your typical wear analysis will not show it, but this will. Now, all of those instruments are, as I said, modular. So they're available in build-up packages, if you will. They're all called the Minilab. So you can have a Minilab 23 with a viscometer and an oil analyzer there. A Minilab 53, which is these two and the particle counter. Or the Minilab 153, which is all of the things here, the full laboratory analysis. So all of those instruments are controlled, and you will see this on a different slide, by 2 software platforms. The platform that actually controls the instruments is called the device console. It's called TrueView, and then the other aspect of it is the archiving database side of it, which is TrueView 360. Now that is available for an off-site manager to schedule analysis, to do all the trending, and that sort of thing. And that is either cloud-based or local server-based, depending on how you are organized in your company. So, for example, a remote manager could schedule an analysis of a stream of assets on a site in another country even. The sample identity and so forth would be sent to the operator of the equipment. He would do the task, upload the data from the instruments, and then that would be compiled and reviewed and trended, etc., by the responsible person for multiple sites and that sort of thing. So it's a very powerful package. So what we'll do now is switch to a different camera angle so I can show you actually the steps taken to do the analysis on all of these machines. Okay, so having explained the overview of the systems, let's now drill down into how we actually perform the various tasks. We'll start with the wear metal analyzer here. First of all, we need to prepare it for analysis. Very simply, we take a graphite disc, place it on the spindle, we take a graphite rod, clamp it in here. This is going to generate our electric spark, which will then excite the atoms in the oil sample, which will be in a little cup just down here. We need to set the gap there. It's very simple. Just drop that down there, lift that lever up, it's done. Now, here's our sample. Obviously, any sample needs to be properly agitated to make sure the particles are in full suspension. I've done that off camera. So, we simply fill this little cup with the oil. It's about 3 mils, but it's just fill the cup, you don't need to measure it. That's that. Get rid of oil sample goes onto this little tray, goes in there, you lift that up, the cup now, the little graphite disc is sitting in the cup. When we start it going, that disc will rotate, picking up the oil, and the electric spark will happen. The light given off will be sent down this fibre optic through the window, through the fibre optic, into the optics of the machine, and you will get the analysis done that way. If you forget to lift that up, or if you forget to set that gap properly, it will tell you you've made a mistake. So we close the door, press the green button, and you will see the spark happening. It takes about 20 seconds, and then that's it done. Finished. We'll look at the results on my screen here. So first thing to look at is the wear metal analysis, and I have the report here of this sample that's failed. Here we have the individual wear metal analysis here. This is silver, aluminium, boron, which is an additive, barium, another additive, calcium, another additive, cadmium, that would be a wear metal, chromium, copper. What is interesting though is the iron at nearly 50 ppm, so that's quite high. Most of the others are relatively low. Zinc's an additive, so that's nothing to worry about. Silicon at 7, I've seen worse, but really I think the thing that stands out here is the iron analysis there. Now, what's important to note with this is that all spectrometers have a inability to measure very large particles of iron if it's an optical emission system. The commercial labs can't really get data on anything more than about 5 microns. We can get data on thereabouts 10, but 20 microns, we just don't see it, and neither does the commercial lab. So that's why our particle counter has the inbuilt large ferrous analyzer as well, so it will pick up anything up to 100 microns. There is a filter that stops larger particles than 100 going through the system, but if you have larger particles than 100 microns, you probably have a broken machine anyway. So it's really just a set of numbers that go together hand in glove with the other numbers, and it gives the system the ability to offer a diagnosis. So it's looking at a more holistic approach to the whole aspect of condition monitoring by oil analysis. Okay, we've already measured the wear metal content of the sample on the spectrometer. Now we need to do the viscosity, oil chemistry and particles. So I'll draw up a sample with the 60 microliter pipette. I'll load it into the viscometer, which is ready. I'll take another amount for the infrared and load that into the flip top cell. Get rid of the pipette tip. I need to just click the infrared to say ready to go. And finally, I just need to start the particle count going. So you can hear the peristaltic pump, the particle counter, churning away there. It's drawing up the sample, going through the flow cell, through the pulsed lasers from the cameras, and that will give us our ISO codes. It will give us our total counts in various particle sizes, and also image the particles into the classical wear shapes, whatever it finds. Not only that, it finally does a large ferrous and total ferrous analysis. This is the part that takes, I would say, the longest, 2 or 3 minutes perhaps of the whole thing. Other than that, you can see now, or I can see anyway, on the device console screen that the oil chemistry side has finished and reported its numbers, so I can be cleaning that out, ready for the next sample. This oil is quite viscous, so the more viscous the oil is, the slightly longer it will take going through the viscometer bore. So I think this is around about 200 centistokes, thereabouts. Of course, I wouldn't be just standing here waiting, I'd be doing something else in real time. That beep is the particle counter saying it's just about done with processing the sample, and shortly it will ask me to start the flushing cycle to flush out the old sample ready for the next. You do that with this flushing solvent here, which is guaranteed to be minimum particle count. You can see now that the viscosity measurement has finished. It's just under 200, so I wasn't far wrong with my guess. And we can clean up the viscometer. As you can see, the viscometer is very simply 2 halves of an aluminium plate with some sensors that form a tube, and the oil dribbles down there past the first sensor and triggers the final sensor when it gets to the end, and that's how it calculates the viscosity. These are heated to 40 degrees, of course. Now, the second beep you heard was the particle counter telling me it's time to start the flushing cycle. So I simply take the oil out, give the probe just a little wipe, put it into the solvent, press the continue button on the device console, cap off my sample, that will start in a minute or so. There we go. So that will flush the flow cell until it detects a minimum amount of particles in that flow cell. That is editable, you can change that. So it will, how long it takes depends on how dirty the sample was that you just put through. If it's a fairly clean sample, the flushing cycle is quite quick. If it's a very dirty sample, which looking at this, I'd be surprised if it's clean. It's going to take a bit longer to flush, but we're talking of the odd minute here, not half an hour. So these units are now ready for the next sample, whatever it may be, that will be sent down from the TrueView platform by the system manager, ready to go. I think we're getting there. Third beat, just about done. It must have been quite dirty. There we are, finished. And I can see, yep, quite dirty and lots of big particles in it as well. So what I'll do now is upload this to the cloud with the upload button, and then we can look at the actual report in a bit more detail, but we'll switch to a view where you can see the screen. Okay, we've done the analysis. We're looking now, if you can see my pointer, at the device console screen. This is what the instrument operator will see. The sample that has just been measured, the instant data here, but there's no recommendations, no anything. These are just numbers for the operator to upload up to the TrueView software itself, but it's like a summary of the analysis that he's just done. So there's all the numbers, viscosity, some oil property here, the particle counts, ISO codes, and the wear index here with cutting wear, sliding wear particles, and some images here of the wear shapes themselves. What the operator then did, that I did, and you didn't quite see, was to press the upload button, and these numbers should have gone up to the cloud. Let's hope that's happened. Let's have a look. There's our sample there, and it's at the moment in the untested area, but we need to put it into the pre-diagnosed. I hope that up button happened. Yes, it did. These are series of samples I've been looking at, but it's this one here. The dash 54 is the one you've just seen me do. That's the testing date, 21st of April, and some alarm codes. It's saying we have, Houston, we have a problem, to use the old cliche. So what we can do now is to have a look at that report. Just click that, and we get the report opened up there, and here it is. So immediately you can see an alarm has been flagged, a big alarm. That's a fail, not a warning, or you would get a green tick if it was okay, but now we have the big fail. You've got some observations here, and it's telling you that the ISO code 4 is severely high, and ISO 6 is severely high, and also 14. We suspect the source of particulates to be dirt, dust, or perhaps a worn seal, because there were some fibers in the images too. Recommended actions: clean the system, oil by filtration or centrifuging. So you're given some guidance of what to do. So here are the actual numbers then. As I said, date. In a real situation, you would put in asset operating hours and oil operating hours and other information, which unfortunately I wasn't in receipt of, but this is what you would do in a real situation, so you can track the length of service of the oil and that sort of thing. Alarm flag here, fail, and the what have we got here? Greater than 20 microns fatigue wear particles, a lot of those, and quite a lot of iron in there, in total iron. And as you can see, what is it, 453,000 odd particles per mil in the greater than 4 microns, and over 34,000 in the greater than 6 microns, and 139 of the big ones. And then we've got some large particles here. Better to look at the images though. There we can see the cutting wear pieces. We've got this sort of curly shape that you get with cutting wear. Sliding, a more flat piece. I mean, I'm not a tribologist, so I'm just reading out what it says. But fatigue wear, some big pieces here. Non-metallics, this would be the dust that the diagnostics mentioned. These are particles that are greater than 20 microns, so that's big particles, plus some fibers as well. The reason it can tell dust from metal particles is you always get a translucent. This would be the silicon crystal. The laser light can get through it, so you see this sort of translucent part. And there we have it. That is immediate diagnosis done in a few minutes on site with recommendations, actions, etc., etc. I hope you enjoyed it. Thank you.